This presentation will cover concepts related to constructing one-sample t-confidence intervals. Note that this presentation is not meant to replace your reading of section 7.1.4 in the textbook. While watching this presentation, it would be very helpful if you follow along in the corresponding portions of section 7.1.4. Lastly, please note that you are responsible for reproducing all parts of this presentation on paper according to our course guidelines for formatting of written work, except for any portions that appear in italics or any slides within the presentation that are specifically identified as not requiring reproduction. Before watching this presentation, you should already understand that the sample mean tends to follow a normal distribution centered at the population mean value of mu when certain conditions are met. You should also know that we can compute a standard error for the sample mean using the population standard deviation and the sample size n based on results from the central limit theorem. And I've gone ahead and reproduced those results from the central limit theorem down below. This is the formula for finding the mean of the sampling distribution of sample means and the standard error for the sampling distribution of sample means. Two other things that you should already know before watching this presentation. First, you should have a conceptual understanding of the t-distribution and its similarity to the normal distribution. You should also know how to find key values related to the t-distribution using RGuru. So in this presentation, we will look at how to construct a one-sample mean t-confidence interval. The technique will use the same four-step procedure we've been using since Chapter 5, that is, prepare, check, calculate with a sketch, and conclude. These steps are also at the top of page 257 of the textbook. You will need to reproduce all work associated with the example that starts on the next slide. So let's look at our example, which is from the textbook. We're going to identify a confidence interval for the average mercury content in dolphin muscle using a sample of 19 Risso's dolphins from the Taiji area in Japan. The data is summarized in the table below. The minimum and maximum values are going to be used to evaluate whether or not there are clear outliers in the data. Please take note that all measurements of the sample statistics are in micrograms of mercury per wet gram of muscle. So we start with our prepare step. We begin by identifying the sample mean, sample standard deviation, and sample size. And in this case, we can get those values from the table. The mean is 4.4, standard deviation 2.3. Keep in mind that the units for those two values are micrograms of mercury per wet gram of muscle, and then the sample size of 19. The next thing we need to do is determine our confidence level, which we're going to use in this case a value of 95%. Next, we move on to our check step, where we will verify the conditions to ensure that the sampling distribution of sample means is nearly normal. So, looking at our independence condition, we note that since we weren't told that a simple random sample of Risso's dolphins was collected, we can't assume that the observations are independent. Therefore, this condition may not be met. However, for the purposes of this example, we will assume that a random sample of dolphins was collected and proceed as though the observations are independent. Next, we move on to checking our normality condition. Because the sample size is less than 30, we must check the data for clear outliers, and I will do so using z-scores. So below, you can see that I've performed those calculations. The minimum z-score that I calculated is -1 17/100ths, and the maximum z-score is 2 900ths. So, since all observations are within approximately 2 sample standard deviations of the sample mean as shown by the z-scores we just calculated, we believe there are no clear outliers and the normality condition seems reasonable. In passing, I should point out that if we were getting, say, more than 2.5 or 3 standard deviations away from the mean, those would probably be considered clear outliers. Because both conditions, independence and normality, are satisfied, we can therefore assume that the sampling distribution of sample means is approximately normal. We now move on to the third, or calculate step of the four-step process. We now know that the conditions hold from our check step. So we now go about computing the standard error, finding our t asterisk value, and also constructing or sketching the interval. So we start with the standard error. We're going to use our sample standard deviation, S, as an estimate for the population standard deviation in the formula derived from the central limit theorem. So I've shown that work down below, and we come up with a value of 528 thousandths. We're now going to proceed in the calculate step to find the t asterisk value. However, before we can do that, we need to identify the degrees of freedom that we will use for finding the t asterisk value. So by definition, degrees of freedom is just the sample size minus 1. Since our sample size is size 19, our degrees of freedom is 18. Moving on, note that just as we did when finding z asterisk values when constructing confidence intervals for proportions, we're going to need the upper tail area to find t asterisk values. So in our case, we were given a 95% confidence level. So to find the upper tail area, we take that value, subtract it from 1, and then divide that by 2, and we get 25 thousandths for the upper tail area. We then go ahead and use the RGuru continuous distributions probability calculator, probability to values function. We set the distribution equal to the student t distribution. Our degrees of freedom is 18. We set NCP, which I won't cover what that is, center equals 0, scale equal 1. Those are default values that you always set. And then our upper tail area is 25 thousandths, and we get a value from the calculator of 2 and 10 hundredths. Keep in mind that this work I've shown on this slide would be what you would need to write down for your RGuru work when you find a t asterisk value. Now, before I move on to the next slide, I should also point out that I did not show how to use RGuru for finding this t asterisk value because I've shown how to do that in previous presentations and videos. So I'm not repeating that work here. We now move on to the portion of the calculate step where we're going to form a sketch for constructing our confidence interval. Notice that I've started by putting the x-bar and t-axes. Notice I've also given the units for the x-bar axis, and at the center of what I've drawn of the x-bar axis, I've put the sample mean value. I then scale upwards by units of standard error, and then I scale downwards by units of standard error until I've gone 4 standard errors below and 4 standard errors above the sample mean value at the center. Now at this point, I want to inject 2 quick comments. Please note that you don't need to copy these into your notes. The first is that the t-axis scaling has a range of -4 to +4, which differs from the range we used for the z-axis scaling. Secondly, when you scale the variable axis, notice that I rounded my values to 1 decimal place accuracy more than the sample mean value that is at the center. Continuing with our sketch work, the next thing I'm going to do is include vertical lines going through the plus and minus t asterisk values on the sketch. I then label those values below the vertical lines. And next, I shade the interval on the variable or x-bar axis. Now, at this point, we need to go and calculate the endpoints for the interval. So I'm going to go ahead and start by finding the margin of error, which I have shown on the right-hand side of the screen. And I use the formula from our textbook for that. And turning the crank, I get a value of approximately 1 11 hundredths for the margin of error. Notice again that I rounded that value to 2 decimal places, 1 more decimal place than our sample mean value. Next, I calculate the endpoints of the interval. So the one on the left is going to be the sample mean minus the margin of error. When I go through that process, I get a value of 3 29 hundredths. Next, I calculate the right-hand or upper endpoint, and I add the margin of error to the sample mean. When I do so, I get a value of 5 51 hundredths. I then go ahead and add both of those values to the sketch to complete my confidence interval. Now, in closing out our sketch work, going to this last slide here for the sketch work, notice that on the right-hand side, I've now included the 2 ways that we could write the mathematical expressions for the confidence interval. I should point out that the most common method you've seen me use is method number 2, which consists of putting the endpoints of the interval in parentheses as an ordered pair. However, I've shown both methods for completeness because sometimes problem statements might be formatted using method number 1. So let's move on to the fourth and final step of our 4-step process, namely the conclude step. We're going to interpret the confidence interval in the context of the problem. So we would say we are 95% confident the average mercury content of mussels in Risso's dolphins is between 3 and 29 hundredths and 5 and 51 hundredths micrograms per wet gram of mussel, which is considered extremely high. And that concludes this presentation.